Okay, welcome everybody here at our next webinar in our series of introducing our degree programs to you. Today we are going to introduce our Materials Science Master's program to you, and let's get right into it. First, I'm going to introduce our presenters, and then you will hear a short introduction about ELTE and about the Faculty of Science, and then an in-depth introduction to the Materials Science Master's program. Then we will have a Q&A session with our students who are here with us today about their experience at ELTE, and then we will talk about how to apply. You can also ask questions during the webinar, so I would like to say now that if you have any questions, then you can submit them in the chat box below and we will answer them, or you can ask at the end of the webinar. So we have Associate Professor Eötvös Adam with us here. He is an experimental physicist and a researcher and a lecturer at the Faculty of Science. We have two of our students, Camilla and Roman, who are both students of the Materials Science program. They are in their first year of their studies, and they are studying here with the Stipendium Hungaricum scholarship program. My name is Eva Nagy, and I am the international coordinator of the faculty, and I am responsible for both scholarship holders and self-finance students who are studying here full-time at the faculty. Let's go to the next slide. So just a little short introduction of ELTE, if you are not familiar with it. So Eötvös Loránd University, or as we call it, ELTE in short. So ELTE was founded in the 1600s, so it has been around for a couple hundred years now, and making it the oldest Hungarian university. The first faculties to be founded were the Faculty of Theology and the Faculty of Humanities. The Faculty of Theology was discontinued after the 1900s, but the Faculty of Humanities is still around, and currently we have 8 faculties. As you can see in this chart, most of the faculties were founded or have made their own faculties during the 21st century, but the Faculty of Law and Political Sciences was also around for a really long time. Today, ELTE is one of the most prominent universities of Hungary, among a couple of others who are very popular, and in these recent times, it can be said that ELTE is very successful in both research and training as well. In 2010, ELTE was awarded the title Research University for participating in many research projects and having over 70 researchers who are also part of the Hungarian Academy of Sciences, having lectures and participating in other things here at the university. In 2013, ELTE has also gained the title of University of Excellence, which is a title awarded by the Hungarian government to universities that are most prominent in both training and research as well. ELTE has over 100 study programs in foreign languages. Most of them are in English, but you can find others as well. And we have over 3,500 international students as well. A Faculty of Science was founded in 1949. Previously, Natural Science was part of the Faculty of Humanities, so it has been around for quite some time, but it only has its own faculty since 1949. At first, the campus of the Faculty of Science was located near the city center, but since 2001, it is located at the scenic bank of the Danube River, which is now called the Lágymányos campus. And we are sharing our buildings with two other faculties, which are the Faculty of Social Sciences and the Faculty of Informatics. The Faculty of Science has 5 institutes, which are the Biology, Chemistry, Geography and Earth Science, Mathematics, and Physics. All of these are divided into smaller departments, so you can say that all areas or disciplines of natural science is covered here at the faculty. We also have 6 doctoral schools: biology, chemistry, environmental science, earth science, mathematics, and physics. Here at the faculty, we have around 300 international students, a bit more actually, but there is a high number of international students here. On this slide, you can see our available degree programs that are all available for international students here at the faculty. There are 9 master's degree programs, and all of our 6 doctoral schools have their training program and the entire curriculum available in English for international students. There are some top mathematicians and Nobel Prize winners among ELTE alumni and staff. In physics, the Faculty of Science is ranked in the top 100 and 150 on the academic ranking of world universities, and also in the excellence group in the 2013 excellence rankings. The Faculty of Science has well-equipped laboratories in natural science all around. So, as I said, all of our departments are really well-equipped, laboratories, and lots of well-esteemed researchers and many members of the Hungarian Academy of Sciences work here in the faculty, also as researchers or as lecturers, and even supervisors for master students and PhD students for their thesis as well. Both theory and practice are very prominent in our degree programs and in course outlines. There are lectures, seminars, practices, laboratory work, and research for your thesis, and many things like that. Okay, so to study at Faculty of Science, there are some funding options available. For our self-financed students, the tuition fee is 4,190 euros per semester. This is the same for all of our master's programs. There are some scholarship programs available by the Hungarian government. One of them is the Stipendium Hungaricum program, which Camilla and Roman are also a part of. And we have the Diaspora Scholarship, which is for Hungarian students who are living in the Hungarian diaspora with their roots, with Hungarian roots, who can apply for this. And we have the scholarship program for Christian young people as well. Okay, so this was my introduction about ELTE and the faculty. So I would like to ask Associate Professor Eötvös Adam to start that presentation as well. Thank you.
Okay, thank you, Eva, and I also welcome everybody. in the next, let's say, 20 minutes, first I would like to give some information on the structure of this special master's program, the Materials Science Master's Program. And in the second half of my talk, I will give some very short description of the different research, or some of the different research topics that we conduct at the Faculty of Sciences. Okay, so as I was introduced, my name is Dr. Eötvös, and I work in the Department of Materials Physics in the Institute of Physics, so I am a physicist. But as you will see in this master's program, this is a joint program of two different institutes, so the Institute of Physics and the Institute of Chemistry. Okay, so how to get your degree once you are eligible to start your studies here? So where is the place of material science among other sciences? So this is a huge group of natural sciences, and the other end on this schematic image we can see that they are the engineering sciences. Material science is somewhere in between these two ones. So engineering is a fully applied science, and natural science can be also, or can cover a wide range from theoretical calculations, experimental sciences through applied sciences. And material science at ELTE is somewhere here, so we are a little bit more closer to the fundamental researches, which doesn't mean, of course, that we don't have any collaboration with industries. Of course, we have a lot of industrial partners, but we are mainly responsible for the fundamental part of this cooperation. Okay, just let me, something doesn't work properly. Okay, so as I mentioned, this Materials Science MSc program is a very strongly interdisciplinary program, which provides a rigorous education in material science and the fundamental of physics and chemistry. So in the very beginning, after you start your studies here, you have to take basic courses both in physics and also in chemistry. And these courses, of course, offer a very large or wide overview of different types of materials. As we proceed, or as you will proceed during your studies, you will gain knowledge in the chemical and physical properties of different structural materials. And this master's program also introduces a strong insight in micro and mainly nanotechnology, which is very, of course, you know that it's a very, very important issue in these years in the 21st century. This program is also based on lectures, seminars, and practical laboratories. Let me just briefly summarize what it means. So in the first semester, you will study probably together with the Hungarian students, because in our master's program, all the courses will be given in English. So you can build up some friendship or relationship with the Hungarians as well. And from the second semester, you will have to take part in practical laboratories, which means that in small groups, usually in a group of 2 or 3 students, you will visit certain equipment in these departments, and of course with the help of some kind of supervisor or researcher, you will take a 3-4 hour course with real equipments and with real measurements. And we also offer seminars to the students, which means that you have to, of course, with again the help of somebody, a supervisor or researcher, you have to give a short seminar, first on some kind of general topics, which you can choose from a larger list. And then, of course, from the second year, so from the third semester, you have to choose your own research topic, which will be the research topic of your thesis, okay? And as you can read here, the high standard of this different variety of trainings is guaranteed by the highly qualified researchers and also the scientists. So in these departments, there is not a very strict separation between teachers and scientists, because each scientist has to teach, and we are happy to teach the students. And practically all of the teachers are doing some kind of research. So it's very common in these faculty. And the education is supported by a very modern infrastructure, and our laboratories, as Eva already mentioned, are very well equipped. And we cover a huge variety of different research topics. So from the second year, when you will choose your diploma topic or your diploma research, practically you can find whatever you want, what is the closest to your interest. We also have a very large library in this faculty, but of course, as time goes on, now most of the people are using or accessing the literature through the computers, so we can have direct access to all the journals from the main publishers in the world, Elsevier and also Wiley and so on. Okay, and in the next slide, I want to briefly summarize the requirements of a successful admission to the master's degree. So all the applicants must have a bachelor degree in chemistry, chemical and environmental engineering, physics or materials engineering, maybe material science or anything which is very similar to this, which is necessary to include a reasonable amount of natural sciences. Okay, I'm also the responsible person for these interviews with these applicants, and I have a quite positive impression from the previous years that those students or applicants who apply to this master's program have a wide background in material science. And you can see two of these guys here, Camila and Roman, who have already and successfully entered to this master's program last year. So your application package should contain a short CV, the copy of the degrees or certificates of your degrees, the transcript of the results during your bachelor studies, and of course a language examination certificate. And as far as I know, these certificates not need to be translated. They are accepted in most of the European languages. Of course, we have some language requirements as well. So the successful applicant must have a good command of English, since all the courses, laboratories, and so on are given in English in this master's program. It is naturally requirement that you have to speak English. And several kinds of international certificates will be accepted. Okay, so we also require minimum 40 credits from the following topics: physics, chemistry, mathematics, informatics, measuring techniques, nuclear techniques, and so on. However, if you don't have enough credits, there are options or possibilities that they can be this knowledge which you miss by the lack of these credits can be supplemented in the first year by some kind of supplementary courses. So for example, if you are very strong in chemistry, but your physics background is not so strong, you can take some supplementary courses here in physics. So let me just now turn to the general structure of the Material Science Master's Program. As I mentioned, we have basic courses, and these courses will be compulsory courses, which provides a solid background and framework of the program. And after that, you have the option to choose special courses, and we call them semi-optional and special lecture courses, and which means that there's a choice which is restricted to a list. We will have but this list is very wide and very long, so it means that I don't know exactly how many special courses we give, but for sure you can choose those courses which are the closest to your interest. Okay, and as I mentioned, in the end there's a master thesis, and you have to work on your master thesis practically through 2 semesters, but in the last, so in the 4th semester, you have to concentrate just on the master thesis, which means that you have to conduct your own research, but of course with the help of a supervisor. And after that, you have to write your thesis, which actually happens right now for those students who are in the second year. So in May, you have to, at the end of May, you have to submit your thesis. And in June, there's a defense and the final exam at the same time. So it means that you have to make a small presentation, maybe 10, 15 minutes about your diploma work. And after that, there's a final exam. And if you successfully pass these things, you will get your final diploma. So altogether, during the 4 semesters, you have to collect 120 credits, which means that on average, you have to take 30 credits per semester in order to complete the training in 2 years. And I strongly advise to share this 120 credits in equal portions, because otherwise you will not have enough time to write your thesis. So it's not advisable at all to shift these credits to the 4th semester. However, I don't know if it is true at the moment, maybe Eva can help us, but it is possible to extend your studies if somehow you cannot get your final degree after the 4th semester, which means that you can apply to some kind of extension to this Tempus Foundation, who provides your scholarship. But I think we need some certification from Eva later on. Okay, so I want to go to the next slide. Okay, this is the general structure of the credits in our master's program. So these basic or ground courses subjects will cover 20 credits. The compulsory basic course is 40 credits. So totally these obligatory courses can cover 60. The semi-optional courses and lectures, 22. Semi-optional courses, which incorporates seminars. So seminars means that you have to speak in front of an audience, I mean, practically in front of the other students. Maybe once in a semester, it requires 2 credits. We have some other special courses for 6 credits, and diploma degrees 30 credits. So these 30 credits are only for the 4th semester. Okay. So what are these obligatory courses which we provide in the first, let's say, 2 semesters? Of course, we have basic material physics 1 and 2, so it covers 2 semesters for totally 5 credits. We have materials chemistry for totally 6 credits. We have some course on solid state physics and material science, advanced ceramics, nanophysics, biomaterials, polymers, structural investigations 1 and 2, laboratory for structural investigations, chemical practices, and laboratory for material structures. So altogether, these courses will cover 40 credits. As you see, just have a look on the title of these courses, and you can see that we cover a wide range from chemistry through material science to physics. Okay, so this was the introduction and the details of the scheme and schedule of the Material Science Master's program. And in the second half of my talk, I want to shed some light on the different research topics which we conduct in these departments or institutes. As I mentioned in the beginning, I'm a physicist, but I also got some slides from the colleagues from the chemistry faculty or institute. However, of course, I'm not professional in most of these topics. Therefore, at the bottom of each slide, I put the name of the responsible person for the certain research area, also his or her email address. So if you want to get some more information of a certain research topic, I would strongly advise to consult with the responsible person, okay? So sometimes I have some problems in changing the slides. I don't know if, yes, now it is working, hopefully. Okay, so the first slide belongs to the Chemistry Institute, and it is about, of course, most of these researchers are somehow connected to nanosciences and nanomaterials, nanoparticles. They are now very, very popular. And now the first research topic is the nanoparticles prepared by the so-called sol gel technique. And the responsible person is Dr. Katalin Sinko. And here she wanted to demonstrate to all of you that if somehow we change the synthesis parameters of this sol gel technique, we can get absolutely different types of nanomaterials or nanoparticles. For example, we can have octahedron particles, some kind of laminated structures, and also nanorods. And the different shape, why is it interesting for us? Because the different shapes and different morphology of these materials probably can correlate with totally different structural, microstructural, electrical, and magnetic properties. So by changing the structure and the morphology of these materials, hopefully we can synthesize absolutely different materials with different properties. Okay, and the next two slides have some biological connections as well, mainly governed by Professor Eva Kiss, who is the responsible person for this research topic. First, I want to say a few words about the development of advanced drug carriers. Why is it interesting for us? In the modern drug research, the crucial aim is to somehow control, both in space and also in time, the release of a bioactive ingredient in the body, in the human body. So it means that targeting the bioactive ingredient is the most important step. How to do this? The best technique is somehow to protect the drug molecule. Unfortunately, I don't have a pointer. I mean, in this chat program, it's not possible to use any pointers, but if you take a look the left-hand side schematic image, you see that there is some kind of sphere, which is the protecting environment. Mainly, it can be a peptide, and the important drug molecule is in the center. So this protecting sphere, for example, it can be a sphere, can deliver your molecule, so this bioactive ingredient, to the place where it is required. And of course, then the second step, somehow we have to release this bioactive molecule at a certain position within the body. So this is very important. Also, Professor Eva Kiss works on, I have sometimes serious problems changing the slides. Now it is okay. She's also working on some kind of modeling experiment, which is the so-called Langmuir balance technique, which tries to model the real cell membrane. As you see, the upper right, on the upper right image, we have an image of a real cell, so it means that it's very complex. And of course, as a first step, it is very hard to model this very, very difficult system. And in this Langmuir balance technique, they usually apply only a one lipid thick layer, which is seen on the left-hand side. And of course, then we can study how to optimize the surface and the surface chemistry of these layers in order to enhance the drug molecules or the drug candidates to carry through to these membranes. So it's a very difficult but very interesting research area. So if you are interested in this, please try to contact Eva Kiss, Professor Eva Kiss. Okay. The next slide is still belongs to the Institute of Chemists, to the colleagues of Institute of Chemists. And the title is the preparation of and characterization of hierarchical nanoparticles and nanostructures. What does it mean, hierarchical? It simply means that we can synthesize or build up different structures or structures containing different nanoparticles with totally different size, which can be very important in different application areas like diagnostics, drug delivery, also biomaterials, and intelligent and active materials. So it means that somehow we have to combine the different nanoparticles, which have different length scales, as you can also see here in the left-hand side image. That maybe here we have some, for example, we can have some metal organic frameworks, which means that these white spheres denote some kind of organic materials which are bonded by some thinner materials. They are denoted by red and blue. So it means that the advantage is combination of materials on different length scales as a whole assembly can provide very interesting properties. And these unique methods and unique properties and unique building blocks probably will result in very interesting applications. Okay. I'm just pressing my keyboard very strongly to change the slide. Okay, and now, from now, I want to turn to the research fields or research areas which we conduct in the Department of Materials Physics. So they have mainly more physical aspects. On this slide, you can see a very schematic summary of structural characterization by using diffraction techniques. What does it mean? Just very briefly. If somehow we have a beam, let's say, it doesn't matter if it is an electron beam or a neutron beam or a photon, and if it interacts with a piece of material, and these incident particles after this collision or interaction can scatter from the material, and based on the local structure, local atomic structure inside your material, we can get different diffracted patterns. As you can, I'm sorry, I'm moving my mouse, and I always think that you see that if I point somewhere on the screen with my mouse, but it's not possible. So please focus on the upper left curve. So this yellow piece is the specimen, and on the screen there is the diffracted pattern, which usually spheres. But after you integrate these spheres, you can get a so-called diffraction pattern on the right-hand side, which incorporates a spectrum containing very sharp peaks. And from the position and also from the shape of these peaks, by using line profile analysis developed in our institute for maybe 20 years, and it is always renewed. So from this fitting program, by this fitting program package, we can directly obtain different parameters that describes the unique structure of these materials, so of this yellow piece on the left-hand side. What are these parameters? The main parameter is, of course, the average crystallite size, but we can also get very important information on the structural or the defect structure of these materials. Probably you have heard that we don't, in the everyday life, we never meet perfect materials. Any kind of material, a piece of metal, a ceramic, a polymer, and so on, always have some defects. And we can determine the defect density of these materials, defect structure, and so on. Moreover, if you focus on the bottom curve, you can also determine the crystallite size distribution of these materials, because there is no any material where all the crystallites are equal. They always have a distribution, and by applying this structural technique, we can determine what is the distribution of these materials, and you can see it on the bottom curve. Okay, and the responsible person for this is Dr. Gábor Ribárik, and if you are interested, just feel free to send him a message. And on the next slide, we can see a few images on a special battery which contains a cobalt foam. So it's like a sponge, as you see on the bottom right scanning electron micrograph. There are very huge amount of pores and or holes among these cobalt particles, and usually this cobalt surface, I mean the free surface of the cobalt, is usually covered by a cobalt oxide layer. Please focus on the bottom electron micrograph, and on the left hand side, on the colorful images, you can see the atomic distribution. So we can also obtain an atomic distribution of the cobalt and oxide elements or atoms. And as you see, the oxide layer is roughly about 300 nanometer wide. There are these blue dots, which covers the cobalt foam. And what is the advantage of this material if you want to synthesize a battery from this? That it is written here that the capacity of this is practically double the value of the graphite anode. So the classical, let's say the classical battery. And in the upper right image, you can also see that these people who are doing this research can easily apply this line profile analysis on the X-ray diffractograms, as I mentioned previously. So this structural characterization technique is very, very widely used in material science. Practically any kind of material you can characterize by the diffraction techniques. And the responsible person for this is Professor Gubica, who is the head of our department at this moment. Okay. I don't know how much time I still have, but a few more slides. This work, the so-called micromechanics, is a combination of experiments or experimental work and computer simulations, and the responsible person is Dr. Péter Ispanovic. And this is really very fancy. We have a scanning electron microscope here in our laboratory, which is equipped not just by an electron source, but also by an ion source. So we use argon, or no, sorry, not argon, gallium ions in a field ion beam. Why is it good for us? Because inside an electron microscope, or inside the chamber of an electron microscope, there is a possibility to manipulate very precisely. So practically on the nanoscale, you can manipulate with your material by removing some portion of your material by a certain program in order to obtain any kind of desired shape and size, almost. And if your material, which you cut from a bulk piece, is in the nanometric, or sometimes said submicron range, it can have very interesting properties. And at the moment I am turning no, I can do it myself. So I have a video here, which I don't know if you can see it. On my screen it is not started yet. But I want to demonstrate how to fabricate a very tiny, it's called pillar, so it's a cylindrical sample. Unfortunately, the video is, I don't know, can you see? I hope that everyone can see this video. You see, finally I'm playing it again. In the center, we will have this cylindrical sample with a diameter of maximum 5 microns. So the surrounding material was just systematically removed, and after that we can have this very tiny pillar. Why is it interesting for us? Because at the same time, or after the fabrication, inside the microscope, we can apply mechanical tests, which can be a compression or a bending. And if your material is in this very, very small length scale, the mechanical behavior will be totally, totally different from the classical size materials. And we can also, by using these experiments, incorporating or in correlation, it's better to say, in correlation with molecular dynamic simulations, we can obtain what is the governing mechanism of these very unique material properties. And here, on the right-hand side, I just wanted to present a final image of a simulation where these T-shaped symbols, reds and blue symbols, denotes the local structural units in the material, the so-called dislocations. And as you can see, after this deformation procedure, these dislocations are absolutely not randomly populated. There are regions where this dislocation population or dislocation density is extremely high. And there are also volumes or regions in the material which are absolutely defect-free. So it's very interesting for us. Okay, the next slide, as far as I remember, but I cannot move. Yes, it's a totally theoretical work conducted by Dr. Gábor Széchenyi, who is doing some kind of theoretical calculations on quantum computers. Probably you have already heard that Google and other key industrial entities like IBM and so on have already produced the quantum computers, which incorporates a superconductive material. Unfortunately, at this very moment, the largest and the most important disadvantage of the widespread application of quantum computing is that you have to cool your material or this chip to extremely low temperatures, to very few millikelvins. So it's minus 273 Celsius degree. And even at these very, very low temperatures, these quantum computers are, due to the quantum mechanical effects, everything is very, very noisy. So at the moment, we cannot run any long algorithms on these superconducting chips because of the noise. And my colleague the work of my colleague is focusing on the key challenge, how to reduce this noise. Of course, at the moment, by quantum mechanical applications, they try to reduce the noise only theoretically. And after that, maybe there will be some featuring steps towards a more stable quantum chip and later on some kind of quantum computers. Okay. This topic is also very interesting, conducted by my colleague Zsolt Kovács and also by me. I didn't put my name here. We work on this topic together. And the title of this topic is Metallic Glasses. Hopefully, or probably you have heard that beside the classical periodic materials, which occupy maybe 99% of the solid materials in the Earth, where the atomic positions are very well defined and well located, just see the upper left image. There are a few portions of the material, solid material in the world, which are not classically crystalline. They are the so-called glassy materials, where the atoms are almost randomly distributed. Everybody knows such a glassy material. This is the conventional silica glass. These are the classical windows of our buildings. However, if you have some sophisticated techniques, you can produce or synthesize such kind of glassy materials from metals. For example, zirconium, hafnium, copper, cobalt, and so on, usually by the combination of these materials. And if you are successful, or if you successfully synthesize such kind of materials, they will have very, very interesting properties. A conventional piece of metal is usually plastic, yes? A conventional glass, your window is practically brittle, extremely brittle. So or a ceramic, if you just let a piece of glass on a stone, it will immediately break. And here we want to merge or make the fusion of the advantageous properties of metals and the advantageous properties of glasses. And on the bottom two images, you can see that the deformation behavior of these materials are extremely unique. Why? Because if you expose such a piece of material to, I don't know, a bending, compression, torsion experiment, the deformation inside the material usually occurs in a very, very low volumetric or very, very low volume. What does it mean, very low? Maximum 1%. In the enlarged image on the bottom right curve, you can see there is a band or a stripe which crosses practically the whole material. And the name of this stripe is a shear band, which means that the deformation is only localized to these very, very thin bands. The thickness of these bands is in the range of 10 nanometers. So we are again in the nanometric regime. And the rest, which means 99% of the material, so outside of these shear bands, the material practically is not affected by the deformation. So we don't have any structural difference in the rest of the material. The structural difference or the structural changes, which are very abrupt, only occur in the shear bands. Okay, and the last slide of my presentation is one of my topics. is the hydrogen storage, again, of course, in nanomaterials. Everybody knows that the non-renewable energy sources will very soon be eliminated from the Earth, and of course the CO2 emission of our conventional cars and so on is absolutely not advisable to our globe. Therefore, renewable energy sources are absolutely important, which incorporates, of course, solar energy, wind, tide, and so on. However, the largest disadvantage of these renewable energy sources is that they are not evenly distributed in time and also in space on the surface of the Earth. For example, during the night there is no sun, so we cannot use the solar energy during the night. So therefore, it is necessary to store the energy which is supported by these renewable sources. One, and not the only, but one very advantageous possibility is the hydrogen storage. Why? Because hydrogen is the lightest element, of course, among the elements in the periodic table. It has the largest energy per unit mass, and of course, the final product when hydrogen meets oxygen will be the simple water. How to store the hydrogen? The hydrogen can be stored in conventional vessels under very high pressure, also in the liquid state, and there's also a possibility to store hydrogen on the surface of some kind of nanomaterials. And in the middle bottom image tries to explain why this solid state hydrogen storage is the best, because as you can see here, it is denoted what is the average distance between two hydrogen atoms if we store it in a bottle under large pressure, so under 300 under 1 bar, so this is the atmospheric pressure, and 300 Kelvin is the conventional temperature. The mean distance between two hydrogen atoms or molecules is 3.3 nanometers. Of course, as we increase the pressure in this vessel up to 350 bars, of course, the average distance will be much smaller, and at the same time, the energy density per unit volume, of course, will be larger. As you can see, if we apply liquid hydrogen at 20 Kelvin, the average distance will be only 0.36 nanometers. Unfortunately, this storing technique or storage technique is absolutely not advisable. Why? Because it is extremely expensive. To keep a system at 20 Kelvin requires a lot of money. Therefore, we are working on the absorption of hydrogen on the surface of some kind of nanomaterials. And you can see here that in this case, the average distance will be 0.21 nanometers, even at room temperature. And in the end, I just want to mention that even at this moment, there are plenty of cars running by hydrogen fuel in Europe. And also there's a train, it's a train from Alstom, a French company. And this train circulates now in the regular transportation in Germany. So of course, at this moment, we can say that the ratio of the transportation by conventional cars and these hydrogen storage vehicles are 1 to a million, but hopefully it will be the future. So thank you for your attention, and I turn back to Eva.
Okay, thank you very much. So our next session is going to be with our students, and basically, I will ask some questions, and I would like you to answer them, and just to get to know you and your experience at ELTE a bit more. So my first question is, how did you find out about ELTE, and how did you decide that you are going to study in Hungary? So what motivated you to choose Hungary and ELTE?
So I had multiple options in my home country, and it would be easier to enroll there, but I really wanted to get an international studying experience. And besides all the options, the ELTE was the best. University is high-rated European university that is also available for the Stipendium Hungaricum. And since my specialty is materials sciences, I looked at the faculty of science, all the facilities, equipment, and people that are currently working on topics that interest me. And I found that this university is fairly equipped, and there are people that can be good supervisors for my master's degree thesis. So.
Okay, thank you. And how did you prepare for relocating to Hungary? Did it go smoothly? Did you have any trouble? How did you contact university?
So it was a little nervous because of the pandemic mainly. And the visa application process was very easy, so all documents were on the website, and so I should only wait for the information from the application center. And the main problem was connected with the tickets and flights, because during pandemic situation it was very difficult to flow from Russia to Budapest, and there were not direct flights. So I flew through Istanbul. Other problem was connected with the flat, because I like to live in an apartment, so I found it by Facebook group. Also, it was a bit nervous, but I found it. And then there was a 14 days quarantine. And I thought that it will be a big problem, but no, because I could order food by the Tesco and other shops. And after 10 days, I could go out because of the PCR tests, which were free for us, for students, for scholarship students, maybe. So I think that all problems were connected only with the pandemic situation. So, and I think that it went smoothly this time.
I'm glad to hear that you have managed to overcome any obstacles that came into your way while coming to Hungary. And what is your opinion about your studies here? Are you satisfied with the program? Do you find it interesting or useful to you?
About the educational process, so despite the fact that currently there is an online learning, it is still properly organized. Most of the teachers have adapted at this point. They know how to work with online teaching, and subjects are usually correlated with the modern science, since many teachers have a pretty significant background. Some of them worked on large companies, and I actually very enjoy the laboratory practices. Each of them have some story, some background. It is very exciting participating.
And are you participating in anything outside of your studies? I know that because of the pandemic, it's a bit difficult to do sports and things like that, but maybe.
Yes, actually, I didn't have much time to do this, and yes, pandemic makes some problems. So basically I had options, but many subjects, many studies, and lockdown. It was really difficult time for such activities.
Yes, unfortunately, it's really a difficult time for many students, but everybody's trying their best. And do you already know what subject you will work on for your master thesis?
So yes, now I'm working with Professor Jana Gubica, and I try to write my master's degree, and I do some research with connected with the X-ray line profile analysis. So it is very interesting, and I'm very glad that I find this university, and so that I'm here now.
Okay, thank you very much. Is there anything that you would like to say to any students who are interested in applying to ELTE, or any tips and tricks for the application or something like that from your experience?
Maybe about the systems, for example, there are three main systems: Canvas, Neptune, and Moodle system. So in the first semester, we had tests in the Moodle system. So this system are user-friendly, and there is no any difficulties with these systems. Also, I think that it is very important for the students to find this balance between the study and relax. So for me, sometimes it is very difficult.
Yes, I believe so. It can be difficult for others as well. So it's really important. It's a very good advice, actually. So thank you for that. And I think we can wrap this part up and just go for the questions section. I can see that we have received a couple of questions in the chat, and my colleagues have already answered some of them. So if any of our viewers has any questions, then you can just type in the chat now, and I will check if there's any questions that are not answered yet. Yes, so I can see that all of them have been answered. And yes, those who are interested in our chemistry program, we will be happy to see you at our chemistry webinar next week. There is a chemistry master's program, so actually no analytical chemistry as is, but there is a chemistry master's program. So I suggest registering for next week's webinar for those interested. Does ELTE accept Duolingo test score for English language requirement? Unfortunately, no. We can only accept internationally accredited language examinations of B2 CEFR level, at least. So it has to be an internationally accredited language examination. So if we don't have more questions, then I would like to just talk a bit about the application process. And we can come back to the questions later, I think, maybe. Okay, I find my presentation, okay. So I will just talk a bit about how to apply to our program if you're applying as a self-finance student. So for those who are interested in the Stipendium Hungary scholarship, there is a different application platform. But this one, applied at ELTE.hu, is for applicants who are applying for our self-financed program. So on the slide, you can see that how this platform looks, and you can register in the upper right corner, and be sure to give an email address that you use frequently, because this will be our main form of contact, or our primary means for communication. So it's really important that you use an email address that you check frequently. After you have registered, you will receive an email that allows you to continue the registration process, and you will need to fill in your personal details, add a photo of yourself, and upload all your documents that are required for application. The required documents can be found in ELTE's degree program finder. On this website, you can find all of ELTE's available degree programs, the requirements, and lots of specific information about each of them. So I strongly recommend that you check it before application and read everything that you can about the program, and contact us if you have any questions. To apply to the program, you need a bachelor's degree in the previously mentioned fields, like chemistry, physics, or any related field of natural science. It can be accepted depending on the courses that you have completed. That is why we need your academic transcripts as well. And you also have to upload your English language certificate as well. If your bachelor's degree is still in progress, but you will receive it this summer, it's not a problem. Then you can upload a certificate of your university stating that you will finish your bachelor's degree soon. And until that, this provisional certificate is accepted as well. And in this case, you should still upload your academic transcripts up until your latest finished semester. You are also have to upload a CV and a motivation letter as well. It is also required that you upload the bank payment proof of the application fee before the deadline. You can upload additional documents that are related, such as conference attendance or publications, but these aren't mandatory. Once you have submitted your application, and the application period is over, we will begin to evaluate the applications. If your uploaded documents fit the entry criteria, you will be notified of the entrance examination via email, and there will be an entrance examination as well. And once you pass this entrance examination, you will receive confirmation from us and your letter of acceptance within 2 weeks. It will be sent to you through the application platform as well. Around this time, you will receive all necessary information about the enrollment, applying for a visa, life in Hungary, etc. In the meantime, I suggest checking out ELTE's website, because you can find lots of useful information on it regarding life in Hungary, accommodation, health insurance. So it's all of the important details are on the website. So you can see some useful links on the slide, and we are looking forward to receiving your application and seeing you in September. So thank you very much. This was my presentation about the application, and I don't see any more questions. So I think yes, so we will have other webinars in this series as well about other programs. So if you are interested in some other degree programs, then you are welcome to join those as well. Thank you. And I think we don't have any more questions. So thank you for your attention and for attending our webinar. And see you next time. Bye.